Let's explore the foundational principles of statistical thinking. We can view this as a structured process, specifically a three-step workflow. The first step is to collect data. In today's technical world, data comes from many sources. It might be on cloud platforms like Google Cloud or iCloud, stored in structured databases, or even on physical media like USB drives. For instance, an e-commerce sale gets logged in a database, and an analyst must retrieve it. Next, we organize the data. Raw data is often messy. We need to take it from unsorted to sorted. This could mean sorting chronologically, from oldest to newest, or arranging by price. It's also crucial to verify the structure, making sure columns like date and price align correctly. Sometimes, an ETL team provides a pre-organized subset, but you must validate that it's a clean dataset. The third step is to analyze the data to extract meaningful insights. Let's say we look at student marks. A simple analysis might just find the mean or fail rate, but a complex analysis compares performance against peers to find the proportion doing better or worse. Real insights aren't just trivial facts like petrol prices change daily, but understanding the factors driving that change. Now, let's look at the two main branches of analysis. First, descriptive statistics. This is used to summarize a data set when you have data for every individual in a group. Common outputs include the mean, the median, the mode, and the variance. On the other hand, we have inferential statistics. We use this to make predictions about a large population based on a smaller sample. Because measuring everyone is impossible or too expensive, we use tools like confidence intervals and regression models to estimate characteristics with a margin of error. To do this well, we must be careful of traps and develop critical thinking. Always ask, where did the sample come from? And is the claim supported by the entire data set? For example, in advertising, a claim like 99% of dentists recommend lacks context. How many were asked? In marketing, 80% off up to ₹20 sounds big but is heavily capped. If ice cream sales jump 30% after an ad in May, is it the ad or just the summer heat? This brings us to causal claims and confounding variables. A causal claim says one factor directly changes another, but we must remember that correlation does not mean causation. For example, an ice cream launch followed by a 30% sales boost might just be due to summer months naturally driving sales. A confounding variable creates a fake or spurious association between a predictor and an outcome. Look at this classic example. Liquor shops seemingly causing higher crime rates. The wrong conclusion is that the shops cause crime. The real confounder here is population density. Big cities have more people, which means both more liquor shops and naturally higher crime. The shops don't cause the crime directly. To be a good statistical thinker, you must look past the obvious numbers and find the true relationships hiding in the data. Next, we will discuss how to let the data speak while avoiding emotional bias.
Statistical thinking means letting the data speak and making sure we use our brains rather than falling for emotional bias. For instance, your personal experiences, like witnessing a single car crash, should never dictate general conclusions about traffic safety. True analysis must focus on general trends and avoid isolated extreme cases. And if you find your dataset is missing a crucial variable, say population size, a good statistical thinker will request that missing data before forming any conclusion. Now let's look at some real-world inferential examples where full data isn't available. Consider an NGO dog feeding scenario. To distribute food across a city, they can't count every single dog. Instead, they count dogs in a sample area. They then assume uniform density and extrapolate that count to the entire city of Mangalore. While not perfect, it provides a highly functional estimate that saves time and money. Similarly, think about election exit polls. Pollsters survey a sample of voters and then apply those sampled patterns, complete with a margin of error, to predict the final election result before all votes are counted. In contrast, a national census is a descriptive process. It requires 100% coverage because it counts every single resident. This precision is required for high-stakes decisions like allocating the national plan, defense budget, social welfare, and guiding global investment. For these massive resource allocations, approximations are unacceptable. Global investors, for instance, heavily rely on this accurate descriptive data to understand market potential, like India's large youth demographic. To do this work, we need core statistical terminology. The population is the complete set of what we care about, like all 5 lakh data scientists in India. A sample, however, is just a subset selected for analysis, like 50 scientists from tech hubs. The number of observations in that sample is our sample size, n. This is any measurable attribute. It can be numeric, meaning it's measured on a scale, like a salary or petrol price, or it can be categorical, describing a qualitative trait like dog breed or city. The mean or x-bar can be calculated descriptively for the whole population or inferentially from a sample. When picking that sample, we use two main sampling techniques. In sampling with replacement, an element is drawn and then returned before the next draw, meaning the same observation can appear multiple times, like in bootstrapping. In sampling without replacement, once drawn, the element is removed, ensuring each observation appears at most once, which better represents a finite population. Finally, we distinguish between predictive and inferential analysis. Inferential analysis draws conclusions about an unknown part of a present population, like estimating today's average salary using confidence intervals. Predictive analysis, on the other hand, forecasts outcomes that do not yet exist, mapping out future trends like next quarter's Mumbai house prices using historical data and regression models. In summary, inferential statistics help us understand the present population we cannot see entirely, while predictive models attempt to see into the future based on identified variables and historical